Yes. Okay. Let's put it like this. We denote the quotient map from fx to fx modulo phi by pi. So pi of some polynomial f of x is simply f of x modulo phi. And I can consider a specific element which is a pi of the polynomial x. And now, if I consider phi capital X in K capital X, I can substitute alpha and I get 0 because I get phi of pi x, assuming that the degree of phi is more than 1, then pi x is simply the remainder polynomial x. So this is phi of x modulo phi, which is simply 0. So alpha is a root of phi. It means that I can write phi of capital X as x minus alpha times some other polynomial psi of x. Now, what is this this field fx modulo phi? Suppose so it is a field containing a root to the polynomial phi, but you may ask, could I constructed some smaller field that still contain a root for phi? So suppose E is a field such that two things happen. One is that E contains the field F, and two, that alpha is an element in E. So what I would like to know what is the minimal field containing F and alpha. Let's call it, you know what? Let's call it F of alpha. So what has to happen in F of alpha? Clearly, if I take any polynomial and I substitute alpha in this polynomial, I have to get an element in f of alpha, because f of alpha is a field. It has to contain alpha, therefore it has to contain alpha square and alpha cube and so on, but it also has to contain a constant, say lambda, from f times alpha, and it has to contain lambda times alpha plus delta times alpha square, and so on. So it has to contain all polynomials in alpha. What I can also expect, if I have a field containing f and containing alpha, is that, well, alpha has to have an inverse in this field. So for any let's take a non-zero polynomial g, um, 1 over g of alpha also has to belong to f of alpha, right? Because g of alpha has to be an inverse, g of alpha has to be an element in f of alpha, and therefore it has to have an inverse. This means, so if f of alpha and 1 over g of alpha has to belong to f of alpha, it means that for any f and g polynomials in f, the quotient f of alpha over g of alpha, assuming that g is not a zero polynomial, let's say g of alpha is non-zero, or rather g of x non-zero. This quotient f of alpha modulo g of alpha has to be in f of alpha. Okay, so what is the minimal construction I can do for having a field containing f and containing alpha? I can take f of alpha to be simply the set of all quotients f of alpha modulo g of alpha, such that f and g are polynomials over the original field f, and g is non-zero. Right? Of course, you can multiply. Multiply two elements in the field. You can also add two elements in this set, and the inverse of f alpha modulo g alpha is simply, assuming that this is a non-zero element, it means that f of alpha is non-zero. Then I can do simply g alpha the modulo f alpha. Is there any question?
is f alpha, does f alpha equal f small alpha over g alpha just because we chose it in this way, right?
Can you repeat? F alpha, you mean the big F?
Yeah, I mean that big f alpha equals small f alpha over g alpha just because it is our choice.
So big F alpha, this one, is the set of all quotients of the form F alpha modulo G alpha. Right? It's the set, and the reason is that, I mean, I want a minimal field with these two properties, and I kind of I reason about it in two steps. I mean, first I assume that it exists, and if I assume that it exists, I can conclude that for any two polynomials, the quotients f alpha modulo g alpha has to be in this field.
Oh, makes sense, makes sense.
Okay, and then I say, okay, but this set of all quotients is already a field because I have an inverse to an element. I mean, it's very easy to construct to see why the other axioms of a field are satisfied. So you get that f like this guy f capital F alpha is already a field. So it has to be the minimal field containing f and containing alpha. Right? Is this clear?
Yes, thank you.
Okay. Now, now take this take generic polynomials f and g, and do long division by this prime polynomial phi. So it means that I can write f of x as phi x q1x plus r1, and gx as phi x q2 plus r2x. For some polynomials, q1, q2, r1, r2, where the degree of r1 and the degree of r2 are strictly smaller than the degree of phi. Now I substitute in this decomposition, I substitute alpha. Phi of alpha is 0. So I get that f of alpha is r1 of alpha, and g of alpha is r2 of alpha. This means that f of alpha modulo g of alpha is simply r1 alpha modulo r2 alpha. Or in other words, this is r1 alpha times r2 alpha minus 1. But remember, alpha is just a convenient notation for us for pi of x, right? Alpha is simply an element in this guy, which is which is X. I mean, if you think of this field K as the set of remainder polynomials, then alpha is simply the remainder polynomial X. So R1 of alpha is the same as what we denoted in K as R of X. I mean, R1 of X. And of course, K already contains inverses to every remainder polynomial R of X. So this is all to say fx modulo phi is simply equal to f of alpha. And the proof is f of alpha is the minimal field containing f and alpha. So this guy K K must contain f of alpha, right? On the other hand, K is simply the set of remainder polynomials R of alpha. So K is contained in f of alpha. You can take what we denoted here, R of X, and think of it as R of alpha modulo 1, right? So there is a double inclusion. We get K equals f of alpha. Is this point clear? This gives us a very nice characterization of what it means to divide by a prime polynomial. Okay. Now, we had a definition of a splitting field. Or you know what? Perhaps, yeah. Okay. I'll give the definition, then some other example. So I start with the field F. And a polynomial f of x, which does not need to be a prime polynomial. A splitting field for f over big F is a field E containing F such that f splits into linear factors. So you could write it, for example, as f is, just write both ways. F splits to linear factors over E, i.e. F of x is some constant lambda. If f is not monic, I have to multiply everything by some constant, times x minus, say, alpha 1 up to x minus alpha n, where lambda and alpha 1 up to alpha n must be, well, they are elements in E. And 2, E is minimal with this property, i.e. for any let's say you want to put someone in the middle between F and E, for any field, such that F splits over K, we must have K equals to E. Okay, so you cannot do better. I mean, so a splitting field, probably the canonical example that everybody knows is that C is a splitting field of the polynomial x squared plus 1. When I think of this polynomial as a polynomial over R, so how do I see that C is indeed a splitting field of this polynomial? First, I want to see that this polynomial splits, but that's easy. I mean, x squared plus 1 equals x minus I, x plus I in C of x. So the polynomial indeed splits, and B, if K contains R and x squared plus 1 splits over K, then K must contain I, right? I mean, this polynomial x squared plus 1, if it splits, then K contains an element such that this element square is equal to -1, or this element square plus 1 is equal to 0. And this, yeah.
I think there's a question in the chat from Lisa.
Yeah, okay, let me.
Says, will minimal E be unique for F?
I'm not sure I understand the question. You mean in the definition of a splitting field, I suppose?
Yeah, I mean in the second point, when you explained that K should be equal to E, we must be equal to E. My question is like, will this E be the unique minimal for F?
Well,
Or-
unique. Okay, we will show that this is that splitting fields are unique up to isomorphism. But for now, we don't assume it.
Okay.
Okay. So this, but the intuition is of course correct. I mean, this kind of condition number 2 is very strong. So you expect that anything that satisfy condition 1 and condition 2 will be essentially unique. Okay, so just to return to this example of the complex numbers, if I have, how do I show minimal? I mean, splitting is very easy. How do I show minimality? Well, if I have a field that over which x squared splits, then this field has to contain I. And any field containing R and I must contain C. Right? Because C is simply the set of all, let's say, A plus BI, where A and B are real numbers. Now, the second example is, maybe just to connect it to the other definition, C, you can view it as R, as the minimal field containing R and I, right? Now, I can do the same thing that I defined C, I can do with the rational numbers. So take let's call it K. K is the set of all A plus BI such that A and B are now rational numbers. And then I claim that K is a splitting field of the same polynomial x squared plus 1, but now viewed over the rational numbers. Okay, so you could start with the field f equals q and say, well, what is the splitting field of this polynomial x squared plus 1 over q? So of course, x squared plus 1 splits over the complex numbers. But the complex numbers is not the splitting field of this polynomial x squared plus 1 over the rationals. And the reason that the complex numbers in this case is not the minimal field with this property. The minimal field with this property is K. Okay, so I will not repeat the argument, but it's maybe you can take it as an exercise that K is a splitting field indeed of this polynomial, and also K is the minimal field containing Q and I. Okay, so we have like basically three ways to view this, right? You have Q of I. You have the splitting field of x squared plus 1 in Qx. And you have what we denoted as Qx modulo this polynomial x squared plus 1. So this is all equivalent definitions. Is this point clear? I think this is really the heart of the matter, and after that the propositions are very easy to see. Carlos, what do you think?
Yeah, for me it is, yeah. But anyone that, I mean, I always assume that if no one jumps in, everything is clear. But however you prefer, we
Okay.
can also try to say something.
Yes, now. Yeah.
Thanks. I'm a bit confused. Like, which is the relation between splitting field and field extension?
So,
yeah, sorry.
yeah, you want to complete the question?
No. It's that. Sorry.
So a field extension, we did not actually mention that too much, but field extension is simply two fields. I mean, it's like what we call the subfield inclusion. So if you have, so the terminology, field extension is the same as a subfield inclusion. Let's say F into K. Right? It means that K is a field and F is a subfield F is a subfield. So this field extension is a very general term, right? A splitting field is a particular kind of field extension. So, for example, in this in this case, I mean, of course, C is a field extension of Q, because it's a field containing Q, such that the operations are the same, but C is not a splitting field of x squared plus 1, because, well, it's not minimal, for example. Yes, Carlos.
This made me question in the properties of field extensions and subfield inclusion. Basically, if I recall correctly, the multiplication and addition tables for the subfield, which is included, in the field on which it is included into, are shared up to the modulus of the field that is included. Is that correct or not?
Not up to modulo. They are the multiplication tables and addition tables in F are simply restriction of the multiplication tables and addition tables in K to the elements in F, right? I mean,
exactly. Okay. Yeah. Exactly.
So they are simply a restriction.
Sure. Thank you, Madam, for the reminder.
Okay. So this is what we're the kind of landscape we're dealing with. I mean, we have a particular kind of a field extension that we call the splitting field. And the proposition we showed last time for any F in F, a splitting field, there exists a splitting field of F over big F. And let me repeat the proof, because I think it was not completely clear last time. Let's say, without loss of generality, F is monic. I mean, monic or not monic, it doesn't change the possible roots of F. And splitting field only depends on the possible roots of F. So if it exists for monic, it exists for every polynomial. Right? Yes.
Are there any properties in for these kinds of splitting fields, such that, I don't know, we can model them on some way with polynomials or something similar, such that we can disclose which ones are and which ones are not splitting? Like, how can I say it? There was a time where we saw, for example, primitive polynomials. How were they able to generate spaces? And I'm wondering if there's any smart way to actually check splitting fields rather than just decomposing the entire thing into the roots and checking.
Well, we will get to it. I guess.
Okay.
Answer.
Okay. Then it's fine.
But you can see from this example for here that one way to get the splitting field of x squared plus 1 was simply to mod out by x squared plus 1. And the reason is that, I mean, x squared plus 1, when it splits, it splits into x minus I, x plus I. So, and once you have a field containing I, you already immediately split the polynomial x squared plus 1, because if you have I, you have to have minus I.
I see.
Okay, so this, in a way, you take a prime polynomial, all the roots that can, I mean, if you add one root, and I mean, and all the other roots are kind of follow from the axioms of the field that they must be included in the minimal field containing your root, then you got immediately a splitting field. That's kind of
okay. Okay, I kind of get the intuition, but don't want to take over more time. So if we'll get there,
okay.
I'll patiently wait.
Yeah, that's okay. It is natural not to understand fully a notion. I mean, of course, we didn't prove anything about it yet, and even after you prove, you only understand it formally. So you have to be patient. I mean,
Sure.
it comes over time.
Makes sense. Thank you, Matan.
Okay, so I write fx as f1 x up to fk of x, where f1 up to fk are prime. But prime, you always need to have a reference field, so prime over f, or over fx. Okay, this is the kind of the prime decomposition, analogous to the prime decomposition of an integer. Now I consider fx modulo f1. This I call k1. Then f1 has a root, let's say alpha 1 in k1. So over k1, I can write, now I'm not going to carry out this capital X, but if you want, you could make it. I'm just going to write f1 of x equals x minus alpha f prime 1 of x. In k1 of x. And this means, by the discussion we had, is that k1 is in fact the minimal field containing f and alpha, alpha 1, sorry. Right? Now, f1 x, well, if f1 prime x splits over k1. We take, well, maybe if it doesn't split, over k1, we can take k1 modulo the prime factor say f1 prime of x is equal to I don't know, phi1 prime x up to phi s prime x with phi1 prime up to phi s prime prime polys over k1, take k1 no, let's say k2 being k1 modulo the first prime polynomial phi1 prime. Then k2 will simply be k1 adjoined with some alpha 1 prime, where alpha 1 is a root of phi1 prime. Okay, so and you continue in this way, repeat this process. Since f can have only finitely many roots, we terminate at some let's say kn, in which or let's say sorry, KL, in which f splits completely. We get a sequence of field inclusions. We started with F, and then we added one root. Once we added this root, we continued until some KL. Let's call it K. And each ki plus 1 is the minimal field containing ki and some new root. So alpha I plus 1 of F, in fact. So since in every step of the way we had the minimal field containing the previous field and another root, it means that the last one is the minimal field containing F and all the roots of F of this original polynomial small f. K is the minimal field containing F and all roots of F, i.e. K is a splitting field. For F. Okay, so this is the proof. Is the argument clear? I try to make the exposition a bit. Yes.
Yeah. Hi. So can you go back to the definition of K1, the first one, when you explain this? Yeah, here. Yeah. So maybe it's I missed something on the definition or whatever. But why do you say F1 as a root alpha 1 in K1?
So this is the preliminary discussion we had in this the beginning. Whenever you mod out by a prime polynomial, the resulting field has a root. This is the heart of all of this discussion. Is I take a prime polynomial, right? Phi.
Yeah.
A prime polynomial, and I look at fx modulo phi. That is, fx modulo phi is the set of all remainder polynomials Rx, right? With the mod arithmetic.
Yeah.
Now I look at the map from all polynomials to polynomials modulo phi. This map is the quotient map or the mod phi map. So I take a polynomial f to f modulo phi. Okay. In particular, I can take the polynomial x. This is a polynomial in f of x, right? I can
Yes.
take pi of x, assuming that phi is of degree bigger than 1. Pi of x is simply x, is the remainder polynomial x, right?
Yes.
But now I can consider phi as a polynomial over k, right? Because k contains a copy of f, namely the constant remainder polynomials, the ones only with a0.
Right.
Right? So if all the coefficients of phi are in f, then they are, in particular, they are in k, and I can consider phi as a polynomial over k. Polynomials over k are kind of a weird creature, because they would be like let's say rk x to the k, but the rk is itself a polynomial, right? But what happens when I substitute in this phi capital X, I substitute pi of x, which I for convenience, I called it alpha. Okay? I substitute pi of x, I get a phi lowercase x. But I mean, of course, I take a polynomial over k, I substitute an element in k, then I have to get some new element in k, right? This new element in k is phi x modulo phi, which is 0. So the conclusion is that phi of alpha, or phi of pi of x, is 0 in k of x. Okay, it's kind of a meta trick, but what I get is suddenly that I have a root of phi in this field. That's the heart of the matter, really.
Okay, makes sense.
Okay, and now I take a polynomial in this proposition. I take a polynomial, I decompose it into a bunch of prime polynomials.
Yes, the rest was clear. It was just this proposition that was like a straightforward thing for me. Okay, but the rest was pretty clear for me. Thank you.
Okay. Other questions before we take a break? All right, so let's meet here in 10 minutes. Sure. So we now come to the second part of the splitting fields properties, namely we want to show uniqueness, but it will be easier to this is a phenomenon that happens a lot in mathematics, that you want to prove something, but it turns out that if you formulate the statement more generally, I mean, if you try to prove something stronger, then the proof becomes easier, because you kind of abstract inconvenient details. So this is the following theorem. suppose rho is a field isomorphism. And let f of x be let's say a n x to the n plus a1x plus a0, and f prime I denote as simply you apply rho on all the coefficients of f. That is rho of a n x to the n rho of a1 x rho of a0, with of course a f a polynomial over the first field and f prime a polynomial over the second field. Let E be a splitting field of f over big F, and E prime a splitting field of F prime over big F prime. Then there exists a field isomorphism. Let's call it sigma from E to E prime. And not only that it is an isomorphism, it restricts to when I restrict sigma to F, I get the original isomorphism rho. Right here inside of E, we must have F, and inside of E prime, we must have F prime, and we started with the map rho. So the claim of the theorem is that you get a map, a field isomorphism sigma, that extends the original isomorphism rho. Okay, it's that's the theorem we want to prove. So the way to go about it is by induction. By induction on the degree of f, which is n. Yeah? The note, this is an abuse of notation, but it's very natural to do. Rho from f x to f prime x. If you take a polynomial whatever sum ai x to the I, then rho simply applies the original rho between f and f prime. It applies it on the coefficients. So this is sum I rho of ai x to the I. In particular, when I apply rho on f, I get f prime, what we denoted as f prime. Now, let's make two observations. One is that rho is a ring isomorphism. I mean, you clearly get I mean, rho respects addition and multiplication because you simply apply the original rho on the coefficients, and the original rho is bijective. So this extended rho must also be bijective. I mean, is this clear? Why this extended rho is a ring isomorphism? Okay, so and then the second observation is a bit more involved. I say that if px is a prime factor of f of x, then when I apply rho on px, I get a prime factor of a rho applied on fx, which, as said, this is f prime x. Now, why is this second observation true? Rho is a ring homomorphism, so it commutes with a multiplication of polynomials. So if I write fx, I mean px is a prime factor of f, so I can write fx equals px times qx for some polynomial qx. And then I apply rho on f of x. It's the same as applying rho on px times qx. And since rho is a ring homomorphism, I get that this is rho px times rho qx. And this is, of course, f prime of x. So what I get is that rho px is indeed a factor of f prime of x. Now, why is this a prime factor? if it's not a prime factor, so let's say if a row of px equals to ax times bx, or maybe we call it a prime x times b prime x, with a degree of a prime and degree of b prime bigger than 1, or sorry, bigger or equal to 1. And of course, a prime and b prime are polynomials over f prime. Then remember, rho is a ring isomorphism, so it means that I have a map in the other direction. This map in the other direction, I know how it looks. I mean, assuming that the original rho was like from f to f prime, I had the original rho being an isomorphism, then it means that I have a map in the other direction, again a field isomorphism, which we typically denote as rho minus 1, such that the composition in each order is the identity map. And if I have rho minus 1 on the level of fields, I have rho minus 1 on the level of polynomials, right? Like we would have rho minus 1 in this direction between polynomials, where you simply apply rho minus 1 on all the coefficients of a given polynomial in f prime of x. And we are guaranteed that rho minus 1 is also a ring homomorphism. So now if rho of px was not a prime polynomial, it would be a product of two, I mean a non-trivial product of polynomials a prime and b prime in f prime of x. And then I apply rho minus 1 on rho of px, I get, well, on one hand, since rho is the inverse, I get p of x, right? And on the other hand, since rho of px is a product of two things, I get that this is rho minus 1 of a prime x times rho minus 1 of b prime x. And rho minus 1 is simply acting on the coefficients, so it preserves the degree. Whatever the degree of a prime and b prime was, the degree of rho minus 1 of them is the same. And a degree of rho minus 1 a prime and the degree of rho minus 1 b prime is bigger or equal to 1, which cannot happen since px is prime in f of x. Okay, is this point clear? We claim, this is the claim, that if you give me a prime factor of f, and you apply rho, you apply the map between polynomial rings that is induced by the original isomorphism rho, then if you apply it on Px, you get immediately a prime factor of rho of the original polynomial f of x. Okay, so this is the basic observation. And now, let's suppose first that f splits to linear factors sorry, that f splits to linear factors over big F. Then this is the best case. We don't have to do anything. Then I take E to be F. This is a split. It's already a splitting field. Of F. And E prime equals F prime is a splitting field of F prime. And then I need to define, I mean, that's kind of the claim of the proposition. I need to define a map sigma that restricts to the original map rho. But here, in fact, I have equality. So set sigma equals rho. And of course, sigma is an isomorphism of splitting fields. Okay. This is if the original polynomial f splits over the original field capital F. And otherwise, let Px be a prime factor of f of x. With, of course, with degree bigger than 1. I mean, if it's a prime factor of degree 1, then it means that I mean, f splits at least into px times another thing. So if we assume that f does not split to linear factors, there is at least one prime polynomial of degree bigger than 1. I let f1 be polynomials over f modulo px. I think our notation is this modulo p. Since rho of px is prime in f prime x, we also have a field which I will denote as f1 prime. This is, you take f prime and you mod out by rho of p, which we know is a prime polynomial. Note that we have a field isomorphism I'll denote it as sigma, or maybe rho 1. It goes from f1 to f1 prime, and it is induced by rho. I mean, you take any remainder polynomial in f, and you apply rho on the coefficients, and you get a remainder polynomial modulo rho of p. Okay. If you want, we can. I mean, we can check the details of why this is a field isomorphism. I mean, we need to show that that it respects addition and multiplication for R and S, two remainder polynomials in F1. Again, F1 is f of x modulo p. Then I take rho of R plus S. It's simply a rho of R plus a rho of S. This is by definition of rho. I mean, and the same would go for, I mean, this is kind of a tautological map. I mean, I started with an isomorphism of fields, and now I extended to polynomials, and I extended to polynomials modulo another polynomial, and so on. It always stays an isomorphism. I mean, if you want an inverse to this map, you get you can construct it by taking the inverse of rho and apply it on remainder polynomials in f prime of x. And so on. Now, since a px has a root in f1, px is some x minus a times p1 of x for some A in F1. Similarly, well, now I apply rho on this whole polynomial. So I get rho of P of X. It has to be equal to rho of X minus A times rho of P1 of X. And rho of some polynomial is simply acting on the coefficients. So this is X minus rho of A times rho of P1 of X. So rho of A is a root of rho of P of X. Now, f of X was, was px times something, and px decomposes into x minus a times another thing. So all in all, I get that f of x is x minus a times some f1 of x, and f prime of x is x minus rho of a times f1 prime of x, where f1 prime is simply applying rho on f1. With, of course, the degree of f1 and the degree of f1 prime are strictly smaller than the degree of f. Let's say degree of f1 is strictly smaller than the degree of f. Degree of f1 prime is strictly smaller than the degree of f prime. In fact, these degrees are equal because f and f prime are, f prime is obtained from f by just doing something to the coefficients. So the degrees are in fact equal. But since the degrees of f1 and f1 prime are strictly smaller than the degrees of f and f prime, we can use the induction hypothesis. So by induction hypothesis, there is maybe do it like this. Let E1 and E1 prime be splitting fields of f and f prime respectively. Then by the induction hypothesis, well, of course, over over F1 and F1 prime. So by induction, I have an isomorphism of fields between E1 prime, sorry, between E1 and E1 prime, sigma, that extends the original isomorphism rho. Okay, so and now I claim that in fact E1 is a splitting field not only for F1 but already for F over the original field big F. Why is that? I mean, it contains the I mean clearly F splits into splits over E1 because E1 is a splitting field for F1 over E1 is a splitting field for this polynomial F1 over the field big F1, but over the field big F1, F already splits into x minus a times this lowercase F1. So all in all, I get that over E1, F splits into linear factors. That should be clear. So that's clearly F splits to linear factors over E1. And why is E1 the minimal field in which F splits into linear factors? I mean, I have F, and then I have F1, which is Fx modulo Px. And this is the minimal. This is the discussion we had in the previous hour. This is the minimal field containing the root A. And then what I did, I extended it into a splitting field E1, which is by definition the minimal field containing all the rest of the roots. I mean, all the roots of F1. So all in all, so E1 is the minimal field, or the minimal field in which F splits. Okay, so this is for E1, and the same goes for E prime 1. Similarly, E1 prime is a splitting field of F prime over big F prime. Okay, and we completed the proof, right? So we get some sigma from E1 to E1 prime. They both contain F, and they are splitting fields with respect to F and F prime. And this sigma extends the original isomorphism. Okay, so this was probably the most involved proof, or one of the most involved proofs we saw. Any questions? Let me draw a corollary. A splitting field for F over F is unique up to isomorphism. How do you show that? Well, you simply take, in the previous proposition, in the previous theorem, you take rho to be the identity map between F and itself. Of course, the identity map is an isomorphism, and rho of F is simply F. So we get that any two splitting fields, E and E prime, of F, any two splitting fields must be isomorphic via an isomorphism that restricts to the identity map. Okay, so we get that a splitting field exists and unique up to isomorphism, which is basically the best one could hope for. Of course, uniqueness kind of on the nose is too strong of a property to expect. Okay, I'd be happy to hear your feedback. What may not be clear. Carlos, what do you think?
From my side, all good. At least for now. Maybe when I do a review later, I'll find some things. But for now, everything.
Okay, I mean, the argument is very simple. It just it was kind of the formulation of the theorem was convoluted a bit, but
yeah, I agree. I think it requires some offline time to revisit prior to, yeah, Serena said the same.
yeah. Okay, so it's good that you review the proof again. In the notes, there are slightly more details, and you're always welcome to ask questions in the next sessions. So,
Sure.
but this is I think the idea of the proof should be quite simple. And so what we get is that splitting fields exist and unique. And we are now very, very close to classify all finite fields using this notion of splitting fields. But this will have to wait for the next time. Okay, so have a good rest of your day.
Thanks. You too, Matan.
Thank
Thank you
you.
for the session.
Thank you and take care.